So thanks a lot for the invitation, and it's a great pleasure to be here. It's my first time in India, so it's really special, and I'm happy to talk and to be the opening speaker here. So this is work, deep portfolio optimization with stocks and options, where the deep stands for this machine learning aspect. It's work with my former PhD student, now Dr. Christopher Anderson, and we are in Utrecht University in the center of the Netherlands. So the outline of the talk today, it will be, I'll talk a bit about stochastic control. I like very much nowadays stochastic control. So you make decisions under uncertainty. Uncertainty are the stock prices, for example, or the wealth process. You make decisions under uncertainty, and then you try to optimize some objective function. So at final time, there is an objective. For example, if you think of asset allocation, and we think in a pension plan, in the end, you want to be sure that you can pay the pensions, essentially. And your objective function at final time capital T should be such that it is that with a big certainty you achieve your goal. And typically mean variance portfolio optimization, we will see that's classic. It brought a Nobel Prize to Markovich, and here we try to see how far can we stretch this paradigm with machine learning, as a matter of fact. So how far can we stretch this mean variance objective function? How can we generalize this? And moreover, how can we add options to the story? And I will say a little bit, that's a bit speculative. So not all regulators in all countries allow for options in a portfolio, but still I'd like to show you what options can do. Especially suppose that you have an objective function, a probability density function at final time, which is non-symmetric. Then the use of options can help us to achieve that non-symmetry more easily than only stocks and bonds. I'll say something about the deep learning algorithm, but I won't go into too much details. For one, my student is the expert, of course, in implementing this, and for the second, the details would be in the paper. So there's a paper on the archive, and the details would be in the paper. But so put it like this. But I'll give some details. All right. So if we think of stochastic optimal control, it is of course a very well-established field. Robotics and you name it. There are many aspects in electrical engineering, in other disciplines, and also in finance. So it's an established field in applied mathematics, but also in the engineering disciplines. And the starting point is often something which is called the McKean-Vlasov stochastic differential equation with a control in the drift. So we have our stochastic process. X is our stochastic process. It is our wealth. It's our wealth, and it goes with a deterministic trend. So B bar is our drift term, and it is an integral over time. And there's uncertainty. There's uncertainty in the volatility. And then here we have explicitly our control, U. And the superscript U here indicates that X is controlled. So we have control on our wealth. If you have stocks and bonds, you can decide how many stocks and how many bonds in your portfolio. And this how many, that is our control parameter. And then there's always a functional, capital J, that we'd like to optimize. And capital J is for example, an expected function based on the terminal wealth. Capital T, at capital T, it's a terminal wealth. And often there's something like a running cost that you like to optimize, or running wealth. It will be zero in our case, this one, but sometimes you want to control things over time, all the time steps. And then it is beneficial to add something like this integral over time. And then given, it's a conditional expectation, given that we are now at some point at some time little t, we are at some point x. And little t runs from 0 to capital T, which is, for example, the time that the pension plan becomes active. You should have a sufficient amount of money to get this. Yeah? So mathematically speaking, let's say all coefficients, they behave well. So they behave well. And they satisfy regularity assumptions. Here is this control, and here there's no control explicitly here. So in our current work, of course, we also develop methodologies where there's a control in the volatility, but that's a little bit more complicated. So that is the next step. And then the aim is to find a control in the admissible controls that minimizes or optimizes. It can be minimized, but it can also be maximized if you add a minus sign in front. But to minimize the value function. So if you would like to optimize something like a return, then of course minimizing the minus return is something like how we do it. So we look for an optimal point. We like to find U in our admissible controls so that this one is optimized. This functional is optimized under the uncertainty in the forward process. Well, this is a classical problem. This is a classical problem, especially I write here time consistent. Time consistent means the optimal control at a certain time is also optimal at a time point later. And optimal at a time point later. That is called time consistent. And if we are dealing with a time consistent optimal control problem, we can make use of Bellman's principle of optimality, dynamic programming principle. So we can go backward in time. We start at final time. We know our final time function, independence of x values. And then we go backward one time step per iteration, one time step, and we make optimal choices. And then if we look forward in time from a certain time point, we know that all the choices have been made optimally. So if we later go forward in time and we make a decision, we know that it will be optimal because we did the strategy backward in time. And that's very classical. And then how can we stress this? So how can we go from time consistent to time inconsistent, and how can we make use of machine learning? And the nice thing of time consistent problems is we only need two time steps to make a decision. Time step t plus delta t and time step t. With these two, it's a Markov process. With these two, we can make the optimal decision. Going backward in time, we can make the optimal decision for time step little t if we are already at time step t plus delta. This is not the case if we go for time inconsistency. Time inconsistency means the optimal solution now is not optimal in the future. And a famous saying is always, tomorrow I stop smoking. And then you are the day after, and again, you say, well, better tomorrow I stop smoking. And so then the optimal decision for this time point is not the optimal decision in the future. That is called time inconsistency. And we need to solve then for all time steps simultaneously. Because we cannot isolate two time steps and work with two time steps alone. We need to solve all of them at the same time. And that's where these machine learning techniques come in handy. So that is what I just told you is on this slide. So backward in time is classical, and we will go forward in time. So we distinguish forward in time from backward in time. Backward in time, then we are working with conditional expectations in the dynamic programming principle, and we only need two time steps. So the main tools are the dynamic programming principle DPP and the Bellman principle of optimality. But nowadays, so that is not our invention, but that is the deep BSDE method. That's a famous method from like 5 years ago. And it has been developed in ETH in Zurich. by Arnold Jensen and others, they go forward in time. These methods have been around in the 80s and 90s of the last century, but it was not feasible. It was not feasible to do so. Now, with the increasing computing power and with these machine learning techniques, it is possible to go forward in time. So we will do something forward in time. We will learn and learn and learn by machine learning until we have an optimal policy. So it's a lot, machine learning is often a lot of trial and error in a way. And then by these weights and biases in the neural networks, you can sort of store the optimal trends and the optimal techniques. So that is what we will do. The algorithm is global, so we work for all time steps simultaneously, which is a little expensive. And moreover, we have multiple neural networks. For each time step, we set up a neural network, and they're all glued together with the help of an objective function. So that is a bit how we want to do it. And this is this classical dynamic, mean variance stochastic optimal control. We have a risk-free and a risky asset, a bond and a stock. And we have a time horizon from 0 to capital T. And at each trading time, we will maximize the expected wealth X. So it should be an X, sorry for that. We would like to maximize the expectation of the wealth at final time and also to minimize the risk. So our functional J is then, it is a combination of the expected wealth, the expectation of the wealth given that we have the knowledge up to time little t, minus lambda times the variance of the wealth. And we look for U's over time, so control parameters over time, in order to maximize this. And that is this classical mean variance portfolio optimization. So J measures the investment opportunities, little u is the allocation in the risky asset, how much in the stock and how much in the bond. And lambda is a trade-off between risk and return. It's clear that when lambda is big, we are more interested in reducing the risk, and if lambda is relatively small, we are more interested in optimizing our return. And also sometimes by varying lambda, we can make a Pareto optimal front. But here in this talk, we will fix lambda. And then the difficulty, so this is already a time inconsistent problem. So we cannot use Bellman's principle of optimization here. Because, so if we want to solve this backward in time, the variance of the variance is the variance of the variance with the knowledge up to time little s given the variance up to time the knowledge up to time little t, that is not equal to the variance of xs xt given the knowledge up to time little t. So we cannot go backward in time and come up with the same problem again. Yeah. Of course, this isn't a problem for which an analytic solution is known. So we know the solution from Markovits, for example, and from Merton, mainly from Merton, but we know the solution. So that is nice. But as soon as you deviate from such an objective function, we are sort of lost, because we cannot use the dynamic programming principle, and we have no analytic solution at our disposal. So mean variance optimization, it's well known, but it's time inconsistent. There are analytic solutions, but if we change the objective or the asset dynamics, because it's only when we have geometric Brownian motion for the asset dynamics when we have an analytic solution. So normal returns and normal stock returns. Otherwise, the derivation of the analytic solution would break down. Now, so it's our aim to focus on some more realistic asset dynamics. It can even be historical data. We don't use that. We use model with jumps, so incomplete market. But also, so in Waterloo, there in Canada, there is this group by Peter Forsyth, and they work with historical stock data from the last more than 100 years. So all the features that are in these last 100 years, everything that has appeared, that by means of a bootstrapping mechanism that enters, say, these historical data would enter the learning of the asset returns. So we look at a bit more realistic stock dynamics that include jumps. And moreover, so far I've been talking about stocks and bonds, but now I would like to also add options, financial options to the story. So I'd like to choose from bonds, stocks, and financial options. And then in a complete market, it doesn't make sense to add options because every option can be replicated with stocks and bonds. But we are in an incomplete market with jumps, and we look at transaction costs and other things. So we look at a more general framework, and therefore it is worthwhile to consider these options. Again, the strategy is a sequence of neural networks with the loss function as an empirical objective function, and optimization, so learning this, is done once for the entire problem. For all time steps simultaneously, we'd like to find these U values. Okay, what are we having? Let's get to it. So we have a trader, and the trader is allowed to trade in a risk-free bond, in N stocks, the number N stocks, and in N options. And that is also already a generalization if you think of the classical methodology. By means of machine learning, we can go to higher dimensions. So we can have multiple stocks in our portfolio, and we can have even multiple options in our portfolio. The stocks are time-continuous Markov processes on a complete probability space for completeness. The bonds, so the stocks we call capital S, the bonds we call B, capital B, and the options and the N options we have puts and calls, put and call options. So we call them V superscript I, and the first few will be call options, and the next few will be put options. So the stochastic, the algorithm can choose whether or not to take options, and whether or not to take stocks, etc. And moreover, later we will see that we also choose K as the stripe. Now there's one simplification that we do here. We have all these time steps, and at all these time steps we can allocate different stock, number of stocks, but the options we only do at T0. So we only fix them at T0. We are not dynamically updating the options. It can be a non-liquid market or something like that. So we are not updating, we only have them at time T0. But we don't know yet how many. And we don't know yet which strike price. But that is sort of a static allocation. So it's sort of static. We keep it, and we are not updating it. We update the stocks. The bond comes with the stocks automatically. What is remaining is in the bond, and we keep the options fixed. We set initial values to 1 at T0. For example, all the stock values will be equal to 1, the option value will be equal to 1, and the bond will be equal to 1. We are in a mathematical setting, and we can always scale it to the real value. Okay, well, we know, and we will hear much more about the options later on. So the European, we distinguish call and put options. We only work with European options. It is the holder may buy a share at a prescribed amount K at time capital T. That is the call option. And the put option, the holder of the option may sell shares for a prescribed amount at final time T. So the right to buy or the right to sell. Why would you put these options in your portfolio? Well, there are, we all know there are two important applications for options. One is speculation. You hope that the stock goes up and then you make a profit, or you hope that the stock goes down, then you make a profit. But the main purpose, we will also see that in our algorithm, the main purpose in our methodology will be risk hedging. It serves like an insurance policy. It protects against any adverse movement in the investment. So it is a way to limit risk. All right, So let's define that stochastic control problem. So let's look at our dynamics essentially, at our wealth. And now that little u from before, that will be alpha and beta, alpha, beta, and k. That alpha will be the process describing the amount of stock, and alpha superscript k, the amount of stock, the amount in stock k. So it's alpha times s that we will allocate, the amount. And when k is equal to 0, it's the amount in the bond. And it's a time dependent. You see there's a time dependent, so at each discrete time point we can change alpha. And then the total wealth of the portfolio stemming from the stock and the bond holdings, the total wealth at time little t, little x subscript t, it's alpha 0 times the bonds at t, plus the number of stocks, the sum k runs from 1 to the number of stocks, alpha k sk. Yeah. And of course, this shouldn't confuse you. We need this in our neural networks. I won't go into that much detail. It's the detail in the paper. But this is the informative piece, I would say. Yeah? So that is the wealth at time t from stocks and bonds. And these alphas are to be chosen or to be optimized. And then the portfolio self-financing. So alpha 0 is already given. Yeah? Alpha 0 is prescribed. It's 1 over the bond value times the wealth minus the number of the other alphas times s. So the return on investment from stocks and bonds, so R with subscript stocks and bonds, that is x at final time minus x at initial time. And that is our return, and that is what we will measure. The second part is the amount of option I. So we have beta superscript I of option I in our portfolio. So the wealth of our option I, of our options is the sum. I runs from 1 to n options, the number of options, of this beta I that we can tune only at time 0, times the ith option. Ith option with its ith strike price. And then the return on investment from the static option position, the return from the options is y at final time, y at time capital T, minus y at initial time. Yeah? And so our total return capital R, is the return from the stocks and the bonds, plus the return from the options. That is what we want to optimize. However, we have all sorts of side constraints. We need to satisfy some constraints. And for example, in order to be more realistic, we need to add transaction costs. Every time you change your stocks, you have to add transaction costs. And also non-bankruptcy constraints. A regulator says you cannot go negative with your wealth, for example. If you go negative, you have to stop. And there are all sorts of other important side constraints. So we can rewrite our wealth. Our wealth at the new time step is our wealth at the old time step times alpha 0, the change in bond, plus the sum of the number of stocks, alpha k, the change in stock. And if we write it like this, we can easily add transaction costs to the story. This part here, so the change in alpha over a time step, times s, discounted, we do a discounting, times a value that is the cost, the actual cost, that we call the transaction costs at time point k. And the change in alpha is connected to the transaction cost, and with this discounting, it essentially says we do not pay immediately, but at the end of the trading period, we pay transaction cost with the appropriate interest rate, which is denoted by R here. All right. Of course, the trading cost a fund manager is not happy to change the asset allocation every time. So if you want to reduce the trading cost, it's also a sign of a stable portfolio. And that's also important. And then we have all sorts of constraints. No bankruptcy. So for example, this change, it needs to be positive. So this is an indicator function, provided that the wealth is non-negative. It's provided that the wealth is positive at time Tn, then we can do this. So this is an indicator function that the wealth is positive. So that we add to the story, of course. Other thing, no short selling of stocks. So the alpha should be greater or equal to 0. We can relax this, but we can also put it as a constraint. No leverage. We cannot short sell the bond. So alpha 0 should be greater or equal to 0. No bankruptcy. So if xtn is less or equal to 0, then all positions should be liquidated and we stay with the value at Tn. And positivity of the bond and the stocks part of the portfolio, that is that at initial time, the initial wealth should be non-negative. So all these things have to enter our neural network story. And if you have worked with neural networks, then you would think, okay, how can we include this in our framework? And then an idea could be, and the idea that we also pursue is, we put this as much as possible in the activation function. So we force certain allocations by means of a specific activation. We'll see that later on. Okay, the objective function. I go a bit slow, but in the end I will go faster. So sorry for that. I think it's nice to explain it, and then at some point we see where we land. I hope we get the objective functions. Classically, and in economics, the people use utility functions. How happy are you? So it's an expectation, and with an expectation, you are in a time-consistent framework, and you can use the Bellman principle of optimality. And that's, say, from the 50s and the 60s and the 70s. Then from the 80s, there came the mean variance objective. Yeah? And the mean variance objective, as I showed on a previous slide, it is perfect when returns are normally distributed. When returns are normally distributed, then mean variance is optimal, because a normal distribution is determined by its mean and its variance. Unfortunately, current day asset returns have a fatter tail, so they are not normally distributed anymore. So when returns deviate from normality and the distribution is asymmetric, why not try to only penalize the downside risk and leave the upward potential be? So if we penalize the variance strongly, then we also penalize the upward potential, because the variance is a symmetric measure. We will keep the variance in our objective function because it sort of stabilizes the whole computation. But in principle, we focus on shifting that distribution to the right as much as possible. Yeah? So a good objective function should represent the investor's preferences. Right? And how much risk would be acceptable for a certain level of profit. And our objective function that we denote by capital U, it depends on alpha and beta. It is depending on the law of this return at final time. So it depends on the distribution or the density, the probability density at final time. So we look for a strategy with alpha and beta such that the objective function is maximized. And we try to penalize downside risk by means of the value at risk and the expected shortfall. Where the expected shortfall measures how much mass is there in tails of distributions. Yeah? So and the value at risk is a certain point, a quantile of a distribution, far away in the tail typically. And then the expected shortfall, we have a plus and a minus. The expected shortfall is the expected value of the mass beyond the value at risk. So it's an integral quantity like the mass in the till, on the left till and on the right till. And our objective function would be the expected, the return minus the variance of the return. And then in order to shift this to the right as much as possible, we have to add these expected shortfalls with a certain threshold or a certain threshold P1 and P2. So, and we have three parameters, lambda 1, lambda 2, and lambda 3, and they describe the risk preference of an investor. So how much should this shift preferably to the right? That is governed by this lambda 1, this lambda 2, and this lambda 3. P1 and P2 are in 0, 1, and they control the size of the left and right till. It looks like this. This is our terminal wealth, for example, and we would like to push the expected return, the blue arrow, as much as possible to the right. We'd like to make the variance as small as possible, preferably have it 0, but then our algorithm is not stable currently, so we need some of it. And then we'd like to push this till to the right, because there are the positive returns, and this till as much this as much as possible to the left, because that gives us the small outlier, the small chance of outlier, the reduced chance of outlier. All right, I'm gonna skip this. These are two slides just saying why it's also good to look at the strikes. The strikes. Of course, we don't know exactly beforehand what a different strike makes for an option. So therefore, we also optimize the strikes. So we optimize alpha and beta, but also the set of strikes. So our optimization goals are alpha, beta, and k. So this is essentially what we want to optimize. Yeah, we want to maximize a strategy out of the admissible strategies. Pi is the allowed trading strategies, taking all constraints into account. And we'd like to maximize that objective function. And we'd like to optimize the objective function. The objective function, the law, I'm sorry for the confusion with the little u. The law depending on the return. So the return is the return from the stocks and the bonds plus the return from the options. And from the stocks and bonds, it is the final wealth minus the initial wealth minus the transaction costs. And the return from the options is the return at final time from the options minus the return at initial time from the options. And the new wealth, the wealth at final time, is the initial wealth plus the sum over all these time points of the indicator the wealth should stay positive, of this the change alpha 0 times the change in bond values plus alpha k times the change in stock values. Yeah. And y at t is the sum of beta I vi, where vi is both calls and puts. Okay, if we think about it, so a natural question is the following. Stock values, they run under measure P, under the real world measure. But options, they go under the measure Q, under the risk neutral measure. So we should take that into account. So we should, if we do a model, we should go to the risk neutral measure in order to value these options. We only need to value them at time 0 because we are not updating them at later time. We know the value at final time, of course, it's the payoff, and then we should value them at time 0, and we do that with a risk neutral formula. I think we do that with the cost, but I'm not sure. Okay, we have a given time as 0, and this is our stock dynamics, the stock dynamics that we adopt in this work. It is a drift times time increment, a diffusion times a Brownian increment, and a jump times a jump size. And so this is geometric Brownian motion without the jumps. It would be geometric Brownian motion, and here is the jump process. jump diffusion. And we use a Merton jump, but we can use any other thing. But the nice thing for us as academics is, of course, with this we can look carefully at what happens for different choices of parameters. For a practitioner, of course, you take historical estimates. That's also possible. So we have final time little tn, and we have all these time points in between, from initial time to up to final time. We have all these time discretization, and we generate m samples with Monte Carlo of all these stocks, because we need to train our neural network. Okay? We need to run a lot of samples and see how the optimal objective function develops. Okay? And the neural network learns with the weights and biases what the optimality is. That is offline, but it's an expensive process. Yeah? You need substantial computing time in order to do it. We use empirical distributions for that law in a Monte Carlo fashion, and the discrete scheme is optimized by letting deep neural networks represent the trading strategies and optimizing with a gradient descent. Alright, then we have a sequence of neural networks, trainable parameters, a number of layers, the activation function, and the output of the network should obey the trading constraints, and they are managed by choosing appropriate activation function in the output layer. I will hurry up a bit because I see the time. And so the layers, the weights and biases that we optimize, that is by means of a neural network. I refer to our paper for that. Yeah. We have a trading strategy. It consists of three parts: the static amount invested in the option, the static strike prices, and the dynamic amount invested in each stock. Yeah. So the admissible trading strategies, they are for beta, for K, for alpha. And for alpha, they depend on the stock. This is essentially the same as we just saw. So we optimize our return, and each time point is a neural network. A neural network with only a few layers, but each time point is a neural network. But only at the very final time, we put this activation function in order to exit the constraint sets. Okay, first we do classical mean variance. So I spent the last 4 minutes, 2 minutes, 3 minutes, 1 minute.
Yeah.
Okay. So I spent the last minutes to the numerical examples. This is classical mean variance. The asset process is for now geometric grounding motion, no jumps, no trading cost, no transaction cost, no constraints, because then we have an analytic solution. So let's see how well this optimization with neural network works as compared to the analytic solution. We have the drift of the stocks, and the first one is most beneficial. It has the highest return, 8%, and we have a volatility matrix with correlations, etc., and it looks like this. And here we see this is the analytic solution, and here we see over the epochs, the training epochs, we see the neural network learn the strategy. We see it converges to the optimal solution. The optimal solution in this case is like this. This is our wealth, the expected wealth, and on top of each other are the analytic solution and the neural network solution, and these are the 95% and the 5% quantity. Here also we see the return, and we see blue is the empirical with neural networks, the empirical final PDF, and orange is the analytical one. And we also see that, except for here, they lie pretty much on top of each other. And we also see quite a substantial left tail. Right? Quite a substantial left tail. So there's still a good probability of getting into the negative, of not making it with mean variance. All right. And this is our final experiment. So now we have the jumps. We have the market frictions. We have the transaction costs. We put in the European call and put options We have the no bankruptcy constraint. So in full generality, we try to see what happens with our methodology. We also have this much more general objective function. We take the worst 1% of the portfolio is penalized, and the upper tail, the expected return of the 5% best outcomes is pushed to the right as much as possible. And we have that lambda 1, lambda 2, lambda 3 set as some experts call it. All right, so what is the outcome then? What would be the outcome? This is the overall average allocation in the different. We have 5 stocks. We have for each stock we have 2 options, a put or a call. And what is then the overall allocation? We see that 35% of our money is in these options, in fact, at time 0. And the largest amount, like 55%, and it increases, is in average over in the stocks, in all these 5 stocks. And the bond is, in the beginning it's a bit less, and in the end it grows. And if we zoom out and we look at the individual stocks, the first one had the highest return, and indeed the first one out of the stocks, the first one is allocated the most by the neural network, and the bond is here. And also the options of the first one, they are allocated the most. Yeah. And now, so if we have a return, we think, okay, we can have not so good returns, less than 1.03. We can have returns that are between 3% and 12%. That's 41% of all the trajectories there. Then we have this allocation, and we have the above 1.12, so a high return. Then we have 26% of all the trajectories go in that direction, and we see that for the low returns, the put options help us. For the moderate returns, it is even. So there's a lot of stocks and bonds, and the puts and the call, they are in balance more or less. And for the low returns. For the high returns, we see that the call option works. And that goes automatically with the neural network. I want to stop here maybe. So I want to say something about what do we see. With options, we see a thinner left tail. So if we add options and the more general framework, we see a thinner left tail. We see a higher density around the expected terminal wealth. And we see a fatter right tail of the distribution. All things that are rather beneficial for asset allocation. Right? So the first and the last, they are good because that prevents large losses and encourages large gains. And comparing to the mean variance strategy, we see a fatter left and right tail in mean variance, and that is non-desirable. So concluding my talk in general, slides would be available. What I want to convey is that with these neural networks, we can just be more general. We can be more general in the asset allocation. We can be more general in the high dimensionality of the stocks and options. We can add the options to the story. We are less mathematical. In time consistent. Everything can be analyzed and theoretically considered. That's more difficult here. Adding options makes the distribution more flexible, and it reduces reallocation, so it reduces the trading cost. I didn't show you, but that was one of the slides. We use a sequence of neural networks, and they produce high quality asset allocation strategies in high dimensions. And so we could also trade options in a dynamic setting, but we didn't do that. So I thank you for your attention. I'm sorry I ran a bit out.
Questions? Two questions. One is a question on one of your slides. You mentioned you are using the jump diffusion model. Subsequent to that, you had a statement that said something about the empirical distribution and what. So I wanted to know what that. Are you estimating the parameters from?
No, it's the Monte Carlo. Yeah. Here we prescribed, so in this synthetic portfolio, we prescribed the drift and the diffusion coefficient and the jump coefficient. We can, of course, calibrate it to historical data. We didn't do that here, but with empirical, I mean we use the Monte Carlo. The Monte Carlo
Simulate parts of the.
in order to get to a terminal distribution.
Not with the historical stuff.
Not with this, not with this.
The second question was: is your interest rate you assume to be fixed?
Yeah, we assume it to be fixed, and of course that can be also made flexible.
So the thing is, I was just wondering why this allocation in the bond is low. Maybe because of the use of put options. But one could think that instead of your liquidation being at when X is negative, you could say I move all my portfolio to the bonds when the return actually becomes less than what the bond, when purely bond portfolio would give.
That's a very good suggestion. Yeah, we didn't think of that. Yeah. So so indeed, there are many possibilities. We chose a subset of them, but the flexibility of the framework is also something that.
But also your capital T would, I mean, the kind of examples that you suggested in the beginning, this capital T, the terminal time would be large.
Yeah.
And you may not have liquid options that would be having.
Yeah. So it would be like 30 years or 40 years from now, and it will be expensive to have liquid options there. But again, this is the basic framework. We can always refine it.
So the tenor of your options is a very long time. So
Because
it's not near the actual tenor. Like it's not, well, your capital T is much smaller than the tenor of the options.
It is exactly the same. They are both the same here. But again, it's flexible. So we have in mind pension plans 30 years from now, a person of 35 investing in pension. But you can also think of private wealth, and then it's much shorter time frames. So the framework is the framework, and then we have to tune it to the application.
So like you spoke about the options being fixed at T0. So what would happen if we made sure like the options would apply to like all like points in time?
So then it would be a dynamic strategy. So we would expect a better return. And I think we would expect a better loss function, but we have to be sure that we can still trade the options. So they must not be far out or in the money, and there's nobody wanting to buy it or sell it. So therefore we are a bit careful, and also, but it's possible in principle. But also this setup was very easy quantifiable for us. We understand what happens because it's all controllable still. But indeed, a future generalization would be dynamically updating the options. Okay. Thank you.
So this what? Maybe I'll ask you.
Like,
What was the reason for specifying that you need to have some variance of the target consortium?
yeah, so it is the stability of our algorithm. Indeed, preferably you would not say do anything with the variance, but if we put it to 0, we see that our algorithm suffers. So we need some minimal stabilization there in terms of it's difficult to understand for us.
Oh yeah, I know. You have working like a Poisson process with memory lesson. So if you are having a very long time horizon, should you not also take into account, let's say, the chance that a firm might default?
Yeah. So indeed, it can be made. That is a good idea. What people sometimes do with these type of things is so when people look at historical time series in order to do something with the stocks, sometimes they look at for pension plans, for example. They look at the survivors in the S&P 500 or the survivors in the Dow Jones. But indeed, mismanagement is a big problem.
So in terms of computational complexity, I mean, every time say you add your options or you don't have your options, how much it increases because it's very computational, right?
Yeah. So, but the optimization in the option is only at time zero. So it is relatively reduced as compared to the other. But indeed, if I have 20 time points, I have 20 neural networks. That is then like the deep BSD method does it. This deep hatching, they make you, instead of one deep neural network, they make several shallow